In this video, we're going to talk about polar area. Now, before we get to polar area, I do want to recall some information from Calc 1. A big part of Calc 1 was studying the area under the curve. And many times we started with this example where we have some function. Let's say this is our function here, y equals f of x. And we're trying to find the area under the curve on the interval a to b. Well, we all know by now that that's really just going to be the integral from a to b f of x dx. Now, the reason why this is f of x dx is because we have rectangles under here. We have base times height, and this integral is going to sum up the infinitely many rectangles necessary to come up with the exact area. So if you remember, this was your base, the change of x, and this was your height, f of x, so base times height. And that gave us, again, the area of a rectangle, in which case we went ahead and summed it all up with the integral. Now, for us, in dealing with polar area, we're going to go ahead and have to take a look now at something a little bit different. Instead of the picture that I have from above, I'm going to go ahead and draw now, either using the x and y axes or the 0 and pi over 2 that many times I use. We're going to find the area under a polar curve. So maybe we'll say this polar curve here is r equals f of theta at this point. All right, so now to get the area under it, it's not going to be done using rectangles anymore. Instead, what we're going to do is we're going to find the area from there to there and underneath. You can see as I continue to draw this out, much like the rectangles, we're actually now going to be using a different shape. We're going to be using the area of a sector. An area of a sector. So if you remember back from your trig days, the area of a sector is going to be 1/2 r squared theta. So for us, the area calculation is going to be the integral, and we're going to have the 1/2 r squared in there. But now you'll note, much like up here, it was the x's that were changing. Now it's going to be the thetas that are changing as we go around. So that's going to be where our d theta comes from. So 1/2 r squared d theta to come up with that area. Now, as far as the bounds go, it was pretty easy to see over here the a and the b. Those were x equals a and x equals b. Here it's going to have to be theta equals something and theta equals something because of our differential. And that makes sense because these are just lines right here. And the equation of a line in polar coordinates would be theta equals the angle. So for us, maybe we'll say this is theta equals alpha, and this one over here would be theta equals beta. And of course, these are the ones that I'm talking about right here and right here. So I'll have my alpha and my beta. And this together now will give me the area under the curve given polar coordinates now. Now, the last thing I want to mention before getting into an example is something you'll hear me refer to quite a bit. It's almost like this guy will be swept through, sweeping out the area underneath that curve. So this is where we'll start, and that sweeper will sweep all the way around through beta, giving us that area. Okay, so as I draw a few examples here up on the screen a little bit, make sure you're kind of viewing it in the same way. You start here and view this sweeping around all the way until we get to beta. Okay, so for the first example, we're going to find the area bounded inside this curve. So r equals 2 sine 2 theta. So in one way, shape, or form, you got to be able to figure out what this graph is. And so given our earlier videos, I'm going to assume that that's possible. But for now, for time purposes, I'm going to go ahead and just skip to the end graph, where this is going to be 4 petaled rows, and it's going to look something like this. Your graphs don't have to be spectacular, but they should be close enough to better understand what you're looking for. Now, if we're going to find the area of the 4 petaled rows, what I'm actually going to do is find the area of one of them and then just multiply the result by 4. So I'm going to do a 4 times whatever this needs to be. So now, this inside part, if you remember, is 1/2 r squared d theta. So I'm going to have a 1/2. My r squared would be 2 sine 2 theta squared d theta. So 1/2 the r squared d theta. So now I really just need to focus in on the bounds. So if you remember to what I said just a moment ago, we need to picture a sweeper coming through here, all right? So long story short, you're gonna have these sectors that we're creating as we sweep through. That sweeper is gonna have to start right here in order to begin its progress of going that direction. So it's gonna have to start at theta equals 0. And again, it's going to have to sweep around all the way now, sweeping around all the way until it gets to be right here. And that's going to give us that full pedal up in that quadrant. So it's going to have to sweep from 0 to pi over 2 in order to give us that. So that would be considered the setup for a problem like this. And then, of course, you've integrated stuff like this before, so I'll leave that up to you. But in case you're ever asked for a setup only, this would be the setup for the area of the region bounded by the polar curve given. All right, so we'll take a look at another one here. And again, it's kind of up to you using our earlier techniques to come up with what these graphs look like. This one in particular, we're dealing with a cardioid, and we're dealing with a circle. So the circle is going to be radius 2. Something that looks like this, and the cardioid will actually be something now that looks like this. You can see how it's a cosine curve. It's also got that negative in there, so I know that it's going to be horizontal due to the cosine, and then I'm going to have the opening this direction because of that negative. But again, regardless, you guys can work through those using the techniques we outlined in earlier videos. So we are going to be outside the cardioid but inside the circle. So it looks like we are going to be right here. All of this stuff throughout there. All right, so to get this thing set up, once again, I'm going to go ahead and use some symmetry. I think that's going to be the most efficient way. Even though we're just going to do a setup, I still think symmetry is always a nice tool to take advantage of. So we're going to have a 2. And then if you'll notice here, because of how this is set up, we're going to have a big minus little case, right? Area of the big minus the area of the little that we don't want, okay? So that's where I'm going to have this integral minus another integral. So let me go ahead and get this set up, at least the obvious part I feel at this point. So we have an integral minus an integral, and it's going to be big minus little. The big is clearly going to be the circle. So I've got my 1/2, my circle, d theta. So my 1/2 r squared d theta would be the big, right, the whole circle. And then I've got the little, which would be the cardioid itself. I want to subtract out that part that I don't want. So that's going to be a 1/2. My r squared in this case would be a 2 minus 2 cosine theta squared d theta. So again, 1/2 r from up here squared d theta. All right, so now for the bounds. So using symmetry, let's just go ahead and let me mark off this part right here. I'm not going to pay any attention to this. I'm just going to focus in on that top part up there, okay? So just ignore that. And to get this, we're going to have to sweep out. So now I'm going to start here, and this is where I'm going to sweep out. And it's going to continue up, and it's going to continue to give me those sectors. So you can see here, I would need to start at 0, okay? So I would start down here at 0, and I'd have to sweep out all the way around to pi in order to get every little bit that I needed. So 0 to pi. So what I've got so far, and only this one right here, is going to be this shaded part right here, just that top half of that circle. Now I'm getting ready to subtract out the cardioid. So I'm going to subtract out this part right here. Well, how do I sweep that out? Well, much like this one, I would also again have to start at 0, sweep that all the way around to pi in order to get rid of all of the part that I don't want. So that would also be a 0 to pi. So we've got our 2, because this right here only talks about the top half, so I need to double it to get the bottom. So I've got my 2, then I've got the area of the big, which would be the circle, minus the area of the little, which would be the cardioid, and then starting at 0, sweeping around to pi on both of those.